So this is the formula. I rearranged it a little bit. This is the formula we got at the end of the last video, 8.7 in the textbook, formula 8.7. And this calculates then the solution to that partial differential equation, the Black-Scholes equation, with a given payoff. So let's do an example. We'll start with the plain vanilla, a call, a European call option, which has a payoff of the maximum of either the difference between S and the stock price, S prime. Remember, the variable here for the stock price is the S prime, or 0. Look back over this formula that we got. Remember that the S prime is the variable here that we're integrating with respect to, so that's the variable that gets integrated out. At the end, when we're done this integration, we sub in infinity, sub in 0 for the S prime. There's no more S primes. The S, this S here on the top, that S survives the integration, stays after the integration, and that's where I get a formula that's a function of the S and the time. So, in order to do that integration then, what do we want? Well, I'm going to replace this payoff piece with this maximum, this payoff function. Of course, for stocks before values of the exercise, I'm going to just put a 0 in for this payoff. That's just going to completely eliminate that portion. So if I'm just looking for a place where I'm not integrating 0, then I really just want to start at E. And then I replace this payoff with the S minus E. So basically I have to integrate this in order to get the formula that you get at the page 200 that has the stock and the time in it. So integrating. And the rest of, and there's going to be like about, I don't know, 10 minutes of me integrating this. The steps though that we learn will be useful for the homework that I'm asking you to do. And you'll notice that this is basically a line. So all of the options that we do learn are either lines like put, call, or binary put and binary call. So they're either flat lines or they're tilted lines. So in the end, with these formulas that we'll get, which will be basically this integral done for flat lines and slanted lines, any question we get, like the homework, that's built out of slanted lines and flat lines, you can just build out of the already pre-done formula. You don't always have to do this integration every time you want to price an option. In fact, I guess you really only have to do this integration if you're pricing some kind of a weird option that isn't a straight line or a flat line, something that's curved, which is very unusual. All right, I'm going to break it up into two pieces across this minus sign. Oh, and I lost my DS. So I broke it up over that minus sign because now I'm integrating two things here. This one's just a constant, this E. If it's just a constant, I can bring it to the outside. Done. So now I'm just integrating this E piece raw. This S prime here, oh, that's going to cancel that. So I've broken it up into two pieces and done my simplifying. The reason I broke it up into two pieces is I'm going to use different substitutions on the two pieces, or different techniques on the two pieces. Let's concentrate on one piece at a time. So again, this is just a constant. Let's just concern ourselves right now with this second integral. So I'm going to try and simplify this piece with some substitutions. And the substitutions will look like the substitutions that we did on our way to actually coming up with this formula. So I'm going to let x prime, and I'm using the notation from the book, equal to the ln of s prime. Now, of course, it's a substitution, so I have to differentiate my substitution. That means that dx prime ds prime is equal to 1 over s prime. So that means when I do this substitution in here, this whole piece just swaps out for dx prime. Of course, I've got to change my endpoints. When s prime is equal to e, then x prime is equal to the ln of e. When s prime is equal to infinity, then x prime is equal to the ln of infinity. So the ln of infinity is infinity. We should probably do that with a limit, in proper integrals, but we'll approach this casually enough so it doesn't cause grief. But I've switched these to x's then. Now, when I'm trying to integrate this piece, I'm not actually going to integrate it in the end. In the end, what I want to do is get that n of, I don't want to use x because we've used x before, but let's say n of phi, which was the normal curve. So the integral from minus infinity, so the area under the normal curve is basically what I'm writing down here, to phi. And what do I need here? I need that balancing piece, which is 1 over square root. Oh yeah, it's just this piece, right? And that's e to the minus, it's going to be phi squared. So this is the sort of thing I'm trying to match. Trying to match with my algebra. So if I can find this piece of algebra in my integral, then I can replace it with that known entity of the area under the normal curve from infinity to that phi. So basically, this e is going to be this, or is this e here. I want this whole piece to end up being minus something squared divided by 2. Well, there's the divided by 2. So it looks like, so I want this whole piece here to be equal to that. So our minuses are going to cancel. The 2's are going to cancel. And so let's square root both sides. In the end, this is going to be my substitution. I'm going to say let phi equal to, I'm just basically taking the square root of both sides here. So that's going to get rid of this square root here. get rid of this square root here, and square root this t minus t. Oh, that should be a big T. That should be a big T for expiry time. All right. Oh, what about this? I still have my S prime in here. Well, this I can write as the ln of S minus the ln of S prime, and S prime is just, or the ln of S prime is just X prime. So this is going to end up being my substitution, which of course I'm going to need to differentiate my substitution. Now let's take a look at this here. If I do this, I'm going to need a d phi dx prime. There's going to be an end up minus here. If I go, since this was already squared, it doesn't matter if this piece was squared in the formula. So if it's the positive of that piece squared, or if it's the negative of that piece squared, it doesn't do anything. So I'm going to make it the negative of that piece squared, just so I avoid that extra minus sign. Since I'm squaring the top piece, this squares into the same expression. But when I do my d phi dx prime, there's no negative in front. And yeah, there's negatives here and here, but with the derivative, those disappear entirely. So let's do our substitution. That's going to be d phi dx prime. Now this is just basic plain vanilla what would be as u substitution, and it ends up being 1 over this piece. Nice. So that means I can replace the dx prime, by this thing d phi. So I'm up here, I'm going to replace, let's take this. I'm replacing the dx prime by this piece. Oh, this middle, we're now swapping out to be, well, we're swapping out this to be, what does all this get to become? Oh, our whole reason for doing this is so that this whole thing up top of the E becomes that phi piece. So now this doesn't have any phi's in it, so it can go to the outside. What am I left to do? Oh, I got to switch my endpoints around. So when x prime is equal to ln E, then phi is equal to, well, this whole big thing here with ln E for x prime. Just a plain change your endpoint kind of substitution. When x prime is equal to infinity, this is infinity minus a little something, basically infinity divided by something, it still stays infinity. Now we're going to end up calling this big piece of algebra here, because I don't want to drag this around, we're going to end up giving this a name, a D name, just as a placeholder later on. But we see where it comes about. So this integral, now that looks like my, well, it almost looks like my target. I'm missing a root 2 pi here. We remember, what did we do? We just took this whole piece and we were just working with this piece separately. So now I can replace this whole thing with this. Does that sigma root t minus t trouble me? Actually, the opposite. It's going to end up canceling some of these things off of that side. So let's take our integral. So this is our v, and I'm replacing this whole thing with what we calculated it is right here. Now, nice. That sigma cancels with that sigma. This root t minus t cancels this with this root t minus t. And let me just move some stuff over here. Well, or move some stuff out. This, I'm just going to write there and throw a 1 over top, so that this whole piece here, that square bracketed piece, that looks like, oh, not that square bracketed piece, this square bracketed piece. That looks like our area under the normal curve. This looks like our area under the normal curve from this piece here to infinity. Okay, so yeah, it's Microsoft Paint, but I'll make a point with it. This is supposed to be the normal curve. That's our ugly number that we calculated. What ugly number? I'm talking about this ugly number. So this thing in the square bracket is the area under the normal curve from the ugly number to infinity. So it's this area in here. So if I want to make it into the, that's not quite the n of x. The n of x formula gives me the area from minus infinity to the ugly number. The n of x gives me this piece here. So this piece here. So pencil. That's an area. This area that I have is 1 minus the uncolored white thing. So over here I can replace this whole square bracketed thing by 1 minus n of ugly number. Now this piece, that integral piece is done. And that integral piece, okay, let's go back up to where we were. That integral piece had the e to the, and the payoff was just a number. So if the payoff is just a number, like in a binary put or a binary call, then these substitutions will produce the formula that we want. And well, what's going to happen here? Well, here in this second part, I can't necessarily use exactly the same constants or exactly the same method, because I'm missing this s prime. We have to think of a slightly different way. In the end, we're going to have to complete the square. Okay, this ugly number. Let's take care of this ugly number for a second here. And I'm going to go back to my ugly picture of the normal curve. So this area that I wanted to put is now 1 minus the area under the whole thing. But there's some symmetry here, right? If I go, I need select. That's minus ugly number. Pencil. So I was calling this area 1 minus n of ugly number. But I could also, since the symmetry, this is the same value. So I could just say n of minus ugly number. That means that this thing, if I do that, minus this whole thing is what I'm going to call ugly number. To match the book, let's call that D2. So D2 is equal to minus that ugly number. So let's clean this up. If I bring that minus sign through, that's going to be minus that's going to throw a minus here, make this a positive, undo, undo. Make this a positive, and instead of going ln s minus ln e, I'll just again put them back into the one ln formula. So that's what we're calling D1. So then I can replace this whole piece here with n of D2, n of D2. And then I don't need the 1 minus. So this area is is the number I want. That's the same as n of minus that number. Now this part cleans up really nice, and we'll follow through with the same idea. But I'm going to have to complete the square. So I want to work on this integral. I'm going to try the same substitution as before. So when we did our substitutions, but now when I do that, well, ds prime is going to be s prime on ground level here, s prime times dx prime, and this is still going to be ln of s minus x prime when I do those substitutions. Now last time this canceled out. Oh wait, I still got to do this, right? It's not e anymore. When s prime is equal to e, this is going to be the ln of e. It's still infinity for the same reasons as last time. So here's my substitution. Our problem is that this s prime is still here. We got to deal with that because I want to change everything into x's. What to do? Well, if x prime is equal to ln of s prime, then s prime is equal to e to the x prime. Alright, so now this integral has all x primes in it, and we're integrating with respect to x prime. These endpoints are x prime. Remember, my goal is going to be to try and massage this into our normal curve, area under the normal curve, cumulative area under the normal curve. So common bases, e and e, I can add the exponents. So I could write this as just straight up here plus x prime. Careful. Right here, plus x prime. Alright, Now I've got this expression. Here's going to be my plan. I'm up here in the exponent. I'm going to have to common denominator across that plus sign. Then I'm going to have to make this whole thing equal to something squared. That's going to be my plan. So, common denominator means there. Now, I want this whole piece to be that minus phi squared divided by 2 again. And I want to make that substitution, but the problem is that I've got x primes here and I've got x primes here. So let's just work with this piece. So I'm just looking at the exponent right now. And I guess let's just expand out this whole piece. Now, okay, let's do the same trick here where we say that what's inside the square bracketed piece, or the square piece, plus or minus doesn't matter. So and I'm just looking at this for a second. I want this whole thing to be negative, so I'm going to factor this minus sign right to the outside. That makes this a minus here. Now I'm going to end up squaring this square bracketed thing. When I square this out, as far as x goes, let's lump this into one piece of algebra so it's easy to follow. That square bracketed thing, now I've just got this binomial. When I expand that out, that's going to be x prime squared minus 2 square bracketed pieces plus square bracketed piece squared. So I called this the square bracketed piece, and when I square that piece out, that's what I'm going to get. So this So there's me just squaring out this bracket, but I don't want to square out these things because it's just a lump of algebra without any x's in it. Now I've got, oh, and of course there's an x prime here. Right? There's an x prime piece here and there's an x prime piece here. I want to put those together. Okay, so we've common denominated those two pieces, the x prime and this big piece in the exponent here. We're just working to clean this up. If I took the minus sign to the outside. If we expand this bracket and then absorb this factor of x prime into the x prime bracket. So I've skipped some steps. It would behoove you to work this out on your own as well. And now all we have to do is complete the square with the x prime, because I've got an x prime squared here and an x prime here. When I complete the square, I end up getting this expression with only the one x prime. And these pieces here, that's the part from the completing the square. That's the leftover piece that's here. if we clean those up, these pieces end up simplifying to this expression here. Again, you should check that out on your own. Now let's break this up into two pieces. Go back to 150 here. Across this minus sign. When I break that up in two pieces across that minus sign, I'm going to get, now again, this, once I distribute this minus, that's going to be a plus sign. So I'm looking at this. Let's move it down here instead. So that's breaking it up across this minus sign. Remember, this minus is on the whole outside of the fraction. And now we can see that some things are going to end up canceling out. Oh yeah, some things like the 2 sigma squared t minus t on the top and the 2 sigma squared t minus t on the bottom. This whole thing should clean up to be that plus this piece. Now that's great. Oh, but what is it again? Remember that this is what we had up here in the exponent. So what we had up here in the exponent. So I'm going to take this piece here. And we simplified this. So on top of the exponent is this whole piece here. Now, what does that mean? Well, I'm going to put this as e to the this whole thing and then e to the common base. So all right, now, so that's common base here. This has no x prime on it, so it can go all the way outside of the integration bracket. And we can do a few more things with this e to the ln. Well, let's do that at the end. So now, where are we? We're going to integrate this expression. Well, no, we're actually going to try and compare it to that area under the normal curve, which means I want to make phi, this time I want to make phi squared equal to I want this without the 2. So just like before, I want that equal to phi squared, so I want phi equal to, I'm square rooting everything here. So I want phi equal to square root everything, square root everything, square root everything. Let's take this opportunity to clean up the top here for a little bit. Notice that if I were to expand this here, I've got minus 1/2 sigma squared t minus t and plus 1/2. This piece combines with this piece to make that a plus. So that's going to be our substitution. Again, we have to differentiate our substitution. This will look quite familiar because it's sort of the same thing that we did before. So that's going to be d phi dx prime is equal to just 1 over the denominator here, which means I can replace dx prime with sigma root t minus t d phi. Let's put those pieces in. Times those pieces here. That's supposed to be on ground level. There. That's my replacement. This is my replacement for dx prime. Oh, and we also got to change the endpoints. So when x prime is infinity, phi is infinity. That one doesn't change. When x prime is ln of e, then this should be equal to, or phi is ln of e minus. So I'm taking this whole thing. So this expression, we can clean up, this doesn't have any phi's in it, so I'm going to bring it all the way to the outside. This looks like the normal curve area from this ugly number to infinity. Let's go back to my Microsoft Paint idea. That's the area from that ugly number to infinity. It's a different ugly number than before. But I can make the same argument that this area is just equal to n of minus ugly number. So I'm going to call, so this expression here, let's just throw some brackets around it for a second. That expression there is supposed to equal to n of minus, I'm going to call it minus d1 to match the book, where d1 is minus this number. No, take that back. d1, let me take that back. d1 is going to be equal to minus this expression. So d1 is minus ugly number, so then n of d1 is, that's n of d1 is this area, which is the same area that I want, same number. So I can replace this whole square bracketed thing with n of d1. So that's what that integral will be replaced by. Now this minus is going to come in the, well, let's put this minus in here. That's going to be minus ln, and well, we'll clean that up in a minute. Back up to our v. It's hard to see. This is what we had for our v expression. That's what we had with our v expression, and this piece, that integral, is going to be replaced with our simplification. So I'm going to get rid of that and pop this in. Now there's some things that can cancel. I can see that this sigma cancels. I can see that this root t minus t cancels. This, oh, wait a minute. We did bad things. This 1 over root 2, go back up to this integral here. I needed that piece in there. So to replace this with n of d1, I needed a 1 over 2 root 2 in there. So if I was to place 1 in there, then I'm going to need 1 out front here to balance it. Now this turns into n of d1. I forgot my balancing constant. That means there's a extra root 2 pi here, which is nice because it gets rid of that one on the bottom. We can also do some more cleaning up. E to the ln s is just s, and now I've got e to the r, positive r times t minus t, e to the r negative. All of this disappears. That's our formula for the call. Oh, we just got to go and collect what the d1s are. Where d1 is equal to that expression, and d2 is equal to, we'll find what we made d2. Where's first ugly number? Let's put that minus sign in front, and I can see that when I put that minus sign into the top, so here's D1 and D2. The only difference between D1 and D2 is D1 has a plus, D2 has a minus. An easier way, I think, is that the difference between them is going to be D2 is equal to D1 minus sigma root t minus t, the denominator here. So here's our formula for a call. European call option derived. All right, well, that was a lot. If I wanted to know what the delta is, in other words, if I wanted to know how much stock I should short in a risk-free portfolio, then I would be trying to calculate DVDS. Of course, I've got the formula here for a call option, so all I need to do is differentiate this piece. This will end up looking like, well, like what we did last week. What we did last week, just differentiating this formula with respect to s. Once we've got the actual formula, calculating all the Greeks means just taking the partial derivatives, the appropriate partial derivatives.